So let's really take a good look at microevolution and how it works. So microevolution, as we established using these Hardy-Weinberg characteristics, is something we measure by changes in allele frequencies. And if you wonder why microevolution occurs, then there must obviously be some influences from the environment or from the genetic material itself that cause these things. And it turns out the 4 causes of microevolution are these. Genetic drift is one, gene flow is another, mutations are a third, and then natural selection is a fourth. Now, notice here, natural selection is important because it is a cause of microevolution, but it's only one. It's a mechanism, but it's only one. And so, when we look at all of these, you'll realize that they are different in terms of what they do. The first one of these, called genetic drift, is a change due to chance. In this case, the interaction between the organisms and their environment has nothing to do with the genes, but it is simply happenstance. It's due to chance. And so here's an example for genetic drift. We start with those white and red flowers. That's what we had before. And in this case, in our first generation, as you can see here, the frequencies of these flowers is 70% and 30%, the allele frequencies. Now, how do we actually count the allele frequencies? Well, as you know, each individual is made up of 2 alleles. And so you would actually have to know what they are. Well, clearly, in this case, you know what they are because if it is white, that's the recessive. So that means that this one's got little r, little r. And with these other ones, you don't really know. So what we're doing here is we're simply counting them because we pretend that we do know. And the reason why is we're simply trying to illustrate the point here. So if you count all the big R's, there's in this population, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 individuals, right? 10 plants. And then what you have to do is you have to count the big R's. How many of them are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And then the little r's is 6. Why 6? Well, because if there's 10 individuals and each individual is made up of 2 alleles, then that gives you a total of 20. Now, 14 out of 20 is 0.7. 6 out of 20 is 0.3. Of course, you can calculate it a different way because if all you have is big R and little r, if big R is 0.7, then whatever is left must be little r, right? So therefore that must be 0.3. So that's how you do this accounting. You got to count all the alleles and figure out what proportion there are out of the whole. Now, in this particular instance, we are declaring that 5 of the 10 plants leave offspring. And the 5 in this case are not based on any kind of internal benefit to the plant. There's nothing in this environment that would say red is better than white. This is just coincidence. Coincidence that perhaps all the 5 that didn't work, those are the ones that for some reason died. Random. It's nothing, maybe the lawnmower ran them over. Whatever it is, there are only 5 that left offspring. And based on the offspring, we can now do another accounting. Now, the 5 that left offspring are circled here. 1, 2, 3, 4, 5. Those are the 5 that leave offspring. And this is what the offspring looks like. Just by chance, we do the same kind of counting. We still have 10 plants. We have big R and we have little r. In this case, we have 10 and 10. So whatever happens between this generation and the next, now turn this into 50-50. And then we go on, and by pure coincidence, again, only 2 of these plants leave offspring, those 2. And as it happens, both of those are homozygous dominant, so you only end up with big R and big R in the next generation. So now you have shifted the population so that the only thing that's left is big R. And this is a random occurrence. Now it is rare that the recessive individuals get eliminated entirely from a population, but in this case that's what happened. And this is genetic drift. This has nothing to do with how good the red is, how bad the white is. This is just by chance. Now there are many other kinds of circumstances when this may occur. One of these is called the bottleneck effect. And in a bottleneck effect, you have genetic drift not based on whether something is good or bad, but simply based on position. In this case, position in the bottle. And it happens when the population is dramatically reduced in size. Now, obviously, this bottle business is an illustration. So here you have the original population, and if you look carefully, you'll find that the original population has green, blue, or purple maybe, and orange marbles, right? And either one you pick, they're a nice marble. They have the same size, they have the same weight, everything is the same. The only difference is that the color is changed. Now, based on the position of the marbles, when you tilt that bottle over and you say, okay, I want 5 marbles out of that bottle, well, based on this bottlenecking event, the surviving population looks like this. You only have the blue ones and the green ones left. The orange ones were eliminated not because of being bad or somehow less of a marble or anything like that, but simply based on where they happen to be in that bottle. That's what's called a bottleneck. Now, in nature, you find something like this. For example, on a small island, you have a population of lizards, and these lizards search for food, and the places where they can search for food could be in the shrubs, which is on the ground, or they could climb up the palm tree and look at it in the palm fronds because there's insects there as well. And while they're foraging, the tsunami sweeps across the island, and everybody who happens to be in the palm tree survives, and everybody who happens to be in the shrubs dies. Now, they were all good at getting food. They were just in the wrong place at the wrong time when they got swept away. So in this case, it has nothing to do with how well they were equipped to deal with their environment. They were just unlucky. And that's an example of a bottleneck. A founder effect is similar, because what a founder effect means is that there are a few individuals that found a new colony, and in some cases you find that if only a few individuals carry with them part of the genetic material from the mainland population, let's say, part of that gene pool, then some of the rarer frequencies suddenly become much more prevalent. So if maybe you have one individual in 1,000 with a certain characteristic, but by chance that happens to be the individual that goes with some others and creates this founding colony, then maybe if 10 of them go, now it's 1 out of 10. So you change from 1 out of 1,000 to 1 out of 10 just by chance. And this is the kind of thing that may have happened in places like the Galapagos, where you had a mainland population with a lot of variation, a lot of genetic variation, but only some individuals traveled across 1,000 kilometers to these islands and settled. And they were individuals that only carried with them a subset of the gene pool of the mainland population. And that subset was random. It was not somehow that these were better equipped to deal with island life. They just happened to be the ones that ended up over there. And so instantly, evolution has occurred, because in the founding population, the allele frequencies are different than on the mainland. This has happened in human history several times, and there are a couple of really well-documented examples. One of these is Tristan da Cunha. That's a a very remote island, and if you look at the map, you can see that it's about halfway between South Africa over here, that's South Africa, and South America over there. And the only way you can get to Tristan da Cunha even today is by taking the mail boat from Cape Town. The mail boat goes to Tristan da Cunha. It stays on the island for about 12 hours, and then it goes on to St. Helena, and then it goes on to West Africa. And that boat goes every 6 months, so don't miss the boat because you'll be stuck. There's no airplane that can land there. It's that kind of an island. And so in 1815, 15 British settlers went there from South Africa, and they colonized the island. And at that point, they didn't realize that one of them carried a recessive allele. Only one with one recessive allele. So this individual did not have an eye disease, but they carried a recessive allele for retinitis pigmentosa. Now you start with 15 individuals. That means that there is a limited gene pool now, and these individuals had to interbreed one way or another, and so they probably had relatives, cousins or something like that, get married, and that's the constraint you have. And as a consequence of that, the recessive allele eventually showed up with retinitis pigmentosa. Now, 150 years later, you found that 240 descendants of these original 15 people, they still lived on the island. 4 had the disease, and at least 9 were carriers, and you can figure out who the carrier is because they're parents of the individuals with the disease, right? And that's 6 times what you would normally expect if you went to the Australian mainland. So the incidence is substantially greater on this little island because of this founder effect. And there are various islands where this kind of thing has happened. If you think of Mutiny on the Bounty, and they went to Pitcairn Island, that's in the Pacific. Similar kind of thing, far off the beaten track, and yet there they were. And so they have some of the similar kinds of issues. And so that's how a founder population can dramatically shift allele frequencies literally within just a couple of generations. Now, gene flow is the second one of these types of changes, and gene flow means that populations that are perhaps a little separated still exchange genetic material periodically. And so if you consider, let's say, the people living on the west coast of the US and on the east coast of the US, it used to be that those were 2 very distinct populations. If you go back to, let's say, the 1840s, just before California became a state, you had a lot of Spanish influence here, because this is where people from Spain ended up. They had colonized a lot of places in the Americas, and this is as far north as they came. And you had all kinds of people, primarily from places like Ireland and England, and then some European countries on the East Coast. And those were definitely separate populations. And you still find the demographics like that. If you're looking for a large proportion of the population African American, you would go to the southern states. If you look for a lot of people with, let's say, Ireland or Italy or England or Germany as a background, then you go to New England, perhaps. And so as a consequence of what happened more recently in terms of travel across from one part of the country to another, first by train and then by plane, and now more and more, you'll find that there is now gene flow between these populations. They are no longer isolated, and the differences between them is now beginning to disappear. And that would be gene flow, where the exchange of genetic material from one population to the other and vice versa is going to reduce the genetic differences between these populations. So this mixing, and it's random mixing, that is something that can become a force in microevolution, because the allele frequencies will change with that level of mobility, genetic exchange. So that's gene flow. Now the picture here, this is from an issue of Time magazine a few years ago, What they did here is they created a composite image, computer generated, of 1,000 women's faces. So what they did is they set everybody up in front of a camera, all basically the same way, and they took their photograph, and then they had the computer merge all of this, as if you take the average of every single point in that photograph, in terms of the color, in terms of position, and so on and so forth. And this is the individual you ended up with. So this is not an actual real person. This is a person who is the average of all the ones that they photographed. They photographed people who were Caucasian, African American, Asian, anything. They just put them all together, and that's what you get. So that is a good example of how gene flow is thought to work. It literally averages out the populations. Now, based on these two concepts, one of the things to look at is how exactly the gene pool of one generation is important to that of the next generation. Well, clearly, the gene pool in the next generation is entirely determined by the one from the previous generation. But how does that actually how can that actually be measured? And the term we use to do this is called Darwinian fitness. And Darwinian fitness is not the kind of fitness that you'd imagine somebody displaying if they're in a gym and they're fit and they're tall and they're strong and all that kind of stuff. That's not the kind of fitness we're talking about. We're simply looking at the contribution from one generation's gene pool to the next. And so if we want to contribute to the gene pool of the next generation, there's only one way to do this. The only way to do this is to have offspring. And so if you want any Darwinian fitness, you have to have kids. That's the biological definition. One easy way to do this is simply count how many kids you have. So if you have a Darwinian fitness of 1, that would mean you have 1 offspring, because that means your genetic material has gone over to the next generation 1 time. If you have no kids, that means you would have a fitness of exactly 0. And 0, of course, means that nothing from this generation of your genes is contributed to the next generation. Now, there is a little caveat, because if you're male, that means that if you have one child and that child is a daughter, you are clearly contributing most of your genetic material over into the next generation, except for that pesky Y chromosome. So the Y chromosome is something that if you have a daughter, gentlemen, does not transfer over to the next generation. So yes, you have fitness, but it's not complete. It's not quite 1. It's 1 minus a tiny little bit. For ladies, it doesn't matter, because you have an X chromosome, and if you have a daughter or a son, it doesn't really matter that your contribution is complete. But gentlemen, you have to have at least a son to pass on your your Y chromosome, and a daughter to have passed on your X chromosome. So Darwinian fitness depends on what you contribute to the next generation. If you have no kids, then that fitness is 0. Now lastly, let's talk about the outcomes of natural selection. Would you mind closing that door for me, please? The outcomes of natural selection, based on the principles that we talked about earlier, are obviously some shift in the frequency of alleles in the population. And since we don't want to always do this with math, let's just take a look at actual characteristics here. And here we have a set of rodents. So this is a population of rodents. And these rodents have a fur color that is, either fairly light or fairly dark or anything in between. Kind of like the skin color of humans. Some people are lighter skin color, some people are darker, and then everything in between. Now, normally, when you look at this population, you'll find that it has a normal distribution. Normal distribution means that individual with the lighter color or with the really dark color are relatively rare in the population. Individuals with the intermediate colors are relatively frequent in the population, right? this is how it normally is. This is, for example, how the height in humans is distributed. If you pick 1,000 random humans, you line them up, you find the majority of them is going to be of a certain height, and only few are really short and few are really tall. That's basically a normal curve. That's what we call that. Now, let's take a look at what the environment might do to these individuals. Here is one scenario. The environment changes so that, for whatever reason, the darker colors do better. Why would that be? Well, perhaps there is an occasion that pollution in the environment makes the environment a little bit darker. And so the individuals that are darker are the ones that are less likely to be seen by avian predators. So the bird will come, bird of prey, right? And the light-colored ones on this background, this new background, they will stick out like a sore thumb, and the predators will easily see them and kill them. So that could be one scenario. As a consequence, whenever there are the lighter-colored ones, they get discovered sooner. Therefore, they're going to be eaten sooner. Therefore, they are going to contribute less and less and less to the next generation, and over time, there is a shift. When a shift like that happens, that would be directional selection. Directional selection means that something in the environment changed. So here, this arrow, this black arrow, that is where the pressure of natural selection acts. The pressure of natural selection acts against the lighter color. That's why there's this fat arrow here. And as a consequence of this selective pressure, the population shifts to a darker color. So that would be directional selection. Now, the next instance is called disruptive selection. Disruptive selection, there's also another term that you might encounter. It's called diversifying. Disruptive or diversifying selection. Diversifying, clearly you end up with more than one thing, more than one set of rules. Or disruptive means that we're changing this unity here. And in this case, for whatever reason, the middle of that distribution, that peak, the average, is no longer working so well. So why would that be the case? One example could be that in an area you find either a substrate made of sand, which looks a little bit like this color, and you have a substrate made of rock, which looks a little bit like that color. So if you are a light-colored animal on the rock, that's bad news. If you're a dark-colored animal of the sand, that's bad news. And so if you are a dark-colored animal on the rock, you're fine. If you're a lighter-colored animal on the sand, you'll be fine. Now, what happens to the ones in the middle? Well, the ones that are in the middle, if they go on the sand, they're just a shade too dark, and you can see them. If they go to the rock, they're just a shade too light, and you can see them. And the birds will pick them off preferentially. And they pick them off, and as a consequence of this application of the pressure of natural selection, over time, and this is over several generations perhaps, you will find that you end up with 2 new peaks instead of having 1. Lastly, we have something called stabilizing selection. Stabilizing selection occurs when perhaps neither of the extremes works particularly well. So if it's too dark or too light, it's not going to work. And again, this is a scenario that can happen when you have the substrate change, or when, it's bad if you're too light on this intermediate substrate, and so on and so forth. Now, there are lots of examples for this kind of thing. If you think in terms of stabilizing selection, the birth weight of human babies, for example. If the baby is too small when it's born, it's not so easy to survive because it doesn't have the substance, right? There's a certain problem when you have children born too early, because maybe things aren't quite developed right, or they're just too small and they don't thrive immediately. So that's not so good. If they're too large, then of course the process of birth itself can be problematic. And so as a consequence of having too big be a problem and too small be a problem, we tend to have a fairly narrow birth weight in the United States. So the extremes are no good in this case. And so this is one thing that can happen. Anyway, those are some of the outcomes of natural selection. And you find that whenever you look at a population over time, you will see one of these kinds of things apply. Directional, disruptive, or stabilizing selection. And that's the end of chapter 13.